In the previous video we looked at Newton's first law. In this video we're going to look at Newton's second law, and that's pretty much summarised by the equation you can see there, F equals ma. In words, what we would say is that when an unbalanced force is applied to an object, or when an unbalanced force acts on a mass, probably a better way to put it, it causes the mass to accelerate. Now, just want to link back to Newton's first law for a moment here. You may recall I specifically worded it for Newton's first law that the forces are balanced. So Newton's first law, forces are balanced. Newton's second law, forces are unbalanced. So now we have a situation where a force in one direction won't be balanced by a force in the opposite direction. Now, when we talk about an object accelerating, there are a few different things that it could do. First, it could speed up, so maintain its direction but get faster. Secondly, it could slow down, again maintain its direction but get slower. And thirdly, it could change direction. An example of that would be circular motion that we'll get to in a later unit. Now, if we look at those examples, just want to draw your attention to how these forces will look. If we look at this example again of a car driving along, so in this case we're going to have the car accelerating. So that means that all the forces that we're going to consider, we will again have the weight force down being balanced by the force of the road pushing back up. In this case though, if it's accelerating, if our frictional force is that one there, for it to be accelerating it means there needs to be an unbalanced force. You can see I've drawn this arrow significantly longer than the frictional force, just to really accentuate the point. So in this case, this car would be moving that way with a velocity, but it would also be moving in that direction with some acceleration. Now, the size of the acceleration and the velocity aren't necessarily linked, so that basically goes back to equations of motion that you need to refer to link those two quantities together. If we just look in the horizontal direction here, we have now that the force of the road plus the applied force, Fa, is now going to give us an unbalanced force. So let's call that Fun for unbalanced. And using Newton's second law, we know that that unbalanced force is equal to the mass of the car multiplied by its acceleration. So in this case, we can then figure out what the acceleration of the car would be if we know the size of the force and divided that by the mass. So that would be an example of speeding up. If we have a look at an example of, just going to go with not so much braking, but just taking your foot off the accelerator pedal. So we'll just look at this as a second example. In that case, what we would see is basically the same as we've got up here. So I'll just copy this diagram and instead of having this applied force, we're now going to have that as our diagram. So you notice there's no acceleration for applied force pushing the car forwards, we only have the frictional force pulling back. So in this case, the frictional force is an unbalanced force. So that provides the unbalanced force in this case. And because that frictional force is providing an unbalanced force, we'll again see, as we did before, that the acceleration will be the unbalanced force divided by the mass. In this case though, the car will slow down because, as we said before, velocity is in that direction, but now the unbalanced force is causing an acceleration in the opposite direction. So that's going to cause the car to decelerate. Now, in the case of braking, all it really means is that instead of just having this frictional force, we'd also apply another force in the reverse direction. So say a braking force FB, that's just going to increase the size of that unbalanced force and therefore increase the acceleration. Now, one last comment to make about Newton's second law. When we're dealing with acceleration and force, the constant of proportionality that links them is the mass. So we've already had a look at an application of the equation, but just want to draw your attention to this idea. And the reason why mass is important here is that it has an impact on the force or the acceleration, depending on which one you're sort of most interested in. So by that I mean, if you have a constant force, so if you say applying a force to a car to get it to accelerate, if that force is constant, a heavier object will accelerate more slowly. Which kind of makes sense. If you've got, say, a car and a bus, apply a constant force to both of those, the car's going to accelerate much more quickly because it's got a much lighter mass. Similarly, but in a slightly different way, if the acceleration is constant, so if you want to have two objects accelerating at the same rate, a heavier object will require more force. So just a couple of points there about how mass ties into this scenario. You could even, if you wanted to, look at the proportional relationships here. So we'd say that F is, sorry, let's go with the first one. So when force is constant, acceleration will be inversely proportional to mass. So as mass increases, acceleration decreases. When acceleration is constant, F is going to be directly proportional to the mass.